Welcome to the videos and material for week 11. We're going to spend about one lecture on determinants and invertible matrices again, and then we're going to spend the remainder of this week on our last major topic, eigenvalues and eigenvectors. These are concepts that you're going to see for sure in your undergraduate career. They're going to be in your second year differential equation course, and you'll see them in many other programs in higher level mathematics or mathematical analysis courses. We're going to open by remembering how we found the inverse of a matrix, if we could find one at all. Recall that to be invertible at all, a matrix has to be square. The only time it's possible to be invertible is if you start with a square matrix. And then we introduce the algorithm for starting with the matrix A and finding its inverse. We built a combined matrix of our original matrix, and then we put it side by side with the appropriately sized identity matrix. We then performed row operations with the goal of making the left-hand side into an identity matrix itself, and then what's left is our inverse matrix on the right-hand side. Just to recap that, we'll start with a simple 2 by 2 matrix, and we're going to find the inverse of it. We begin by putting the matrix itself, the A matrix, in, and then the identity matrix, which is the ones down the diagonal and zeros everywhere else. So this is our I sub 2 for a 2 by 2 identity matrix. Now our goal is to make this through row operations into the identity matrix on the left, and one of the ways we can achieve that, let's just keep row 1 for now, and to get rid of this 2 in the left-hand side here, we're going to need 2 R1s minus 3 R2s. That'll be 2 times 3 is 6, minus 3 times 2 is 6, and it'll cancel. So we're going to copy the first row, 3, 5, 1, 0. Then do 2 times this minus 3 times that, that's 0. 2 times 5 is 10, minus 3 times 4 is 12. 10 minus 12 is negative 2. 2 times this minus that, 0 minus 3 times that is negative 3. Moving on, let's take row 1 as is again. So we'll keep it 3, 5, 1, 0. Then this row, let's divide by we need a 1 here, so we're going to divide by negative 2. So we'll take negative 1/2 of row 2. So negative half of that is 1, that's the whole point. Flip the sign, divide by 2 is 1, negative 1. And this one is positive 1.5. I'll use decimals. You can use fractions if you prefer. All right, and that gives us the last row now in the identity matrix form on the left-hand side, which is perfect. Now we've got choices about how we tidy up the first row. We could do the subtraction now with the 5. In fact, yeah, let's do that. Let's do R1 minus 5 R2s. And we'll keep R2 as is. So we're going to copy R2, and row 1 is going to be 3 minus 5 times 0, that's 3. 5 minus 5 times 1, the whole point of that is to make that a 0. Then this minus 5 times that would be 6. This minus 5, that's 7.5, so it'll be negative 7.5. And we're almost there. The only missing ingredient is a leading 1 here instead of a leading 3, so we're simply going to take 1/3 of our first row and keep our second row as is. I'll do the second row first because it's just a copy, and I'll make my 5 look like a 5. There we go. And then we have the 3 divided by 3 is 1, 6 divided by 3 is 2, and 7.5 divided by 3 is 2.5, and negative. And so this is our A inverse, or writing it separately. So A inverse is equal to the matrix 2, negative 2.5, negative 1, negative 1.5. Now again, at first glance, those two matrices, the original A matrix and its inverse, don't look particularly close in their relationship. But if we add one extra ingredient, I think you'll see there's more hiding there. So here's our A matrix again, and the A inverse we just found. And just because it seems relevant, let's find the determinant of A. So the determinant of A, again, this is for a 2 by 2, it's this nice simple rule. We get the diagonal minus the other diagonal, which is 2. And just a reminder, This means that the A matrix effectively scales areas in a 2 by 2 region by a factor of 2. And so the determinant of A inverse will be, well, it has to undo that, so it will be 1/2. It'll be 1 over that 2. And if we start thinking about halves and this part here, well, let's actually factor out a half here. If I look at A inverse and I break out a half, that means I multiply everything inside by 2 to compensate. So I pull out a half, multiply everything inside by 2, -5, -2, and 3. And all of a sudden hey, these are the same numbers. Rearranged a little bit, but these are the same numbers. In fact, what we're going to do here is just move this over for a second. Write our A matrix beside it as 3, 5, 2, 4. And what it looks like is that we exchanged or swapped the diagonal elements, and the off-diagonal elements, the 2 and the 5, became negative. We flipped their sign. So, well, this is not a proof or anything. It feels like there's a relationship here that was sort of hidden by our RREF methods. I mean, we did this calculation, we got numbers, but just looking at the result, it isn't clear how that tied back to the original. Whereas for this 2 by 2 case, it feels like there's something else going on. And it turns out there absolutely is. And what it's going to do is give us an alternative way to construct the inverse. And again, having more methods is often helpful. I'll warn you up front, this process for finding the inverse, so this is an alternative way to calculate the inverse, is complicated, and it's based on determinants. So we're going to see a lot of common terms, common usage with what we use to compute determinants. However, there's a pile of terminology we need to get through. We're going to do this, and we're going to do an example right afterwards to solidify the ideas. All right, so A inverse is 1 over the determinant of the original A, okay? We know how to do that. Compute determinants, maybe tedious, but fine. This other part here, this adj of A, is new, and it's called the adjoint of A. So the adjoint matrix. It appears in other contexts as well, so that's why we're introducing it here, so it's not completely foreign to you. But it does have a complicated definition, and you're going to see multi-stages here. So the adjoint of A is equal to some other matrix C with a T over top here as a transform here. That T indicates a transpose. Now, transpose is a reflection of the values of a matrix along the diagonal, and it's pretty straightforward. So if we had the matrix, let's take our matrix A that we started with, 3, 5, 2, 4, then A transpose is going to equal, we keep the diagonal's the axis of symmetry, we keep it the same, and what we do is we flip over everything on either side. So it becomes a 5 and a, oops, 5 was there before. It becomes the 2 here moves to the other side, the 5 here moves to the other side, and that becomes A transpose. You can often see this done in programming text too, where you have a vector, which might be a row vector, and then V transpose is the column vector version of it. So basically you're flipping things down, flipping things up. So that's the transpose. What is this C matrix? This C matrix is called the cofactor matrix of A, and we don't have a C equals kind of equation. Instead, we have each element of C. And what we're going to see here is, determinants. We have our -1 to the I plus j, and what that is our checkerboard for signs. This is our plus, minus, minus, plus. Start with positive in the top left corner and go, or plus, minus, plus, minus, plus, minus if it's a 3 by 3 matrix, etc. We take that and we multiply it by the determinant of another matrix, Mij, but we've seen this one before. This is the submatrix of A with the row I and column j removed, just like we did with determinants. You've seen all these building blocks except for the transpose before. We're just putting it together to create the inverse matrix in a new way. Let's apply this right away and see how it works out. So we have here our 2 by 2 matrix. So we know the answer already for this from the RREF method, but now we're going to compute the inverse using the adjoint method. A inverse is equal to 1 over the determinant of A, what we started with, times the adjoint matrix of A. And this, we know, this was the 12 minus 10, which was 2. So the determinant of A was 2, so we're going to have a 1/2 in this expression. We need the adjoint of A. Well, the adjoint of A is equal to some matrix C transpose, and with C equaling a 2 by 2 matrix, same size as A, and it's labeled C11, C12, so we're going to find each of the elements of this matrix one by one. And we also have our checkerboard, which is our positive, negative, negative, positive, like so. So C11 is equal to, go back to here, C11 is our sign for the I plus j. Well, it's going to be a positive sign according to our checkerboard, or subbing in I and j here. And then the determinant of the matrix by eliminating the 1, 1 cell. So let's put the positive in here first. We're going to redraw over top of this poor A matrix over and over again. So I'm going to do it here with a tablet, and I'll erase it all the time. Make whatever notations you feel you might need to make. For C11, we're looking for the minor where we're not including 1, 1, we're not including that row, and we're not including that column. So we'd find the determinant of the matrix 4, which is the only thing left here. And the determinant of that matrix is just 4, so this is just 4. So we now know the first element of our C matrix. For C12, that's this element in our checkerboard, or you can use the -1 formula. We're going to have a negative sign for it though. And we're going to need the determinant of, erase everything here. We're now at C12. We do not use that row, we do not use that column, and we have the determinant then of the submatrix, just 2. And that is -2. And we keep repeating. C12 comes with a negative sign, and the determinant of C21. C21's here. We don't want that row or column. And you can see already, I'm writing out more than I have to. If you got into the pattern for this, it's just helpful for illustrating and making sure every step is clear the first time you see it. This time we're at C22. That's associated with a positive sign, positive. Determinant of the submatrix for C22, crossing that row and column out, we get our 3. And so we get +3 for that. So our C matrix is, we just found those 4 values. It's going to be 4, -2, 5, and 3. And that means that C transpose is, and the transpose is keep the diagonal elements the same, 4, 3, and we swap the off-diagonal elements, so the 5 goes up, and we have a -2 down here, and I just realized I forgot a negative sign. Negative here for -5, -5, -5. There we go. And that means that our A inverse is 1/2. There's a determinant, and this is what we call the adjoint matrix for A. We just put that in. 4, -5, -2, and 3. And that is exactly what we found earlier. That is the matrix. If we multiply the 1/2 in if we want to, 2, -2.5, -1, 1.5. Now why is this nice? Because we can apply this in general. If we take a look at the 2 by 2 case with A, B, C, D as our ingredients, if we start with a generic matrix A, B, C, D and look for its inverse using this method, we find a common pattern. Note this is only for the 2 by 2 case. And so let's just recap what we did before. C11, C12, C21, C22. We had our little checkerboard signs of plus, minus, minus, plus. They alternate as we move down or right. And so C11 is a positive something. The other ones have negative coefficients for those two, and then 2, 2 is positive. And then we look up our submatrix. C11, we scratch things out, we get D. C12 is this one, we scratch out rows and columns and we get C. C21 is this one, we scratch out rows and columns, and C2, 2. Scratch out rows and columns gives us A. So for any 2 by 2 matrix, the C matrix that we're building is going to be D, negative C, negative B, and A. And that means that C transpose, again, we're going to keep these the same, D and A, and we're going to exchange things, mirror them across the diagonal. We're going to get a negative B and a negative C, and that's our adjoint matrix for a 2 by 2 case. Wonderfully simple. And that means that, sorry, this is adjoint of B this time as our matrix that we started with. So B inverse is equal to 1 over the determinant of B. And here's that general pattern that we saw before. D minus B minus C and A, where we swap the places on the diagonal. If you take a look at what we started with up here, we had A and D, and now we have D and A. On the off diagonals, we just flip the signs. If we can memorize that pattern for the nice 2 by 2 cases, it means we can quickly find inverses for simple 2 by 2 cases. So if we had our original matrix that we started with, and that we've now inverted several times, we now know how we could generate this very quickly, or its inverse very quickly. Right away, its inverse is 1 over the determinant of this. 2 by 2 case is easy. 12 minus 10 is 2. We swap the 2 diagonal elements. So we're going to get, I'll do them in the colors that match what we did up there, 4 and 3. So we exchange those. And then we keep these as the negative versions, but in the same place. And we're done. So that's worth having in your toolkit. You'll often see it used as a shortcut for computing inverses in this special case of a small matrix.